Thank you, Leslie Boutok, for letting me presenting that presentation. So most of the results that I will show you have been obtained by Jean-Baptiste Chagnulot, the second in this line, who is carrying out a PhD, doing a PhD between France and Portugal with the group of João Coutinho. And so I just add theory and experiment hand in hand in the title because I thought that was pretty. So yes, the objective is to develop greener biphasic systems, more sustainable, for the separation of natural compounds using CPC. The plan will be as following. So we'll have just, of course, an introduction of the strategy, and then several things that we will do both experimentally and theoretically. So I will show you now what I mean. In the context, there is, of course, everybody knows it, so it's a general slide on that. There's a current demand for natural compounds, and when we do a plant extraction, we would like natural compounds or natural solvents, sustainable solvents. Right now, we still use hexane or diethyl ether, and this becomes problematic. So one of the ideas that we have in the group is to develop alternative solvents, and among them, of course, deep eutectic solvents. But we are trying to do it a bit differently than what we have seen here. So compared to several other discussions, we won't be talking a lot about the extraction, which of course we do in the lab, and you all recognize the same strategy that I believe most of us have. We select a raw material, we use a sustainable solvent, then we carry out an extraction, and we analyze the extract. We are focusing right now on the purification of those natural compounds. Imagine you get the extract here, and we want to recover specifically one compound. So what we have to do, because we want at the end of the day to apply that, the whole idea to CPC, we want to use centrifugal partition chromatography to selectively separate compounds. We have to go through all this process. So first phase diagram, because we want new systems, biphasic systems, which is often a combination of different solvents. We need, of course, to know what the phase composition of our biphasic system is. Then partition coefficients of a natural compound. Here I show you coumarin as an example. And then we can apply it to this CPC purification. All the first arrows are also done, are also modeled, described, and sometimes predicted using Cosmotherm. So in the whole presentation, we will go through these 4 arrows, both experimentally and theoretically. So just very short on the CPC, it's actually a rotor that contains kind of a column or a decanting column, a column with a series of decanting cells, and you have a stationary phase in blue and a mobile phase in yellow. So if you have a biphasic system, you can have one phase that will be the stationary and another one that will be the mobile phase. Because compound partition differently, they will move through the mobile phase like that and will elute differently. So we have an elution and a partition at the same time. And this is how we can separate different compounds. For example, the blue, the black, and the red one. When we do that, of course, we have to go through the whole arrow that I showed you before. We have to do that experimentally. It's very tedious, time consuming. And what we try to do is to develop a modeling tool of these complex extraction systems. So what we want is to predict what solvents to use for what natural compounds, and to gain a better understanding into the extraction mechanism. Because if we understand it better, we can anticipate, or we can predict better what solvent for what natural compound. So this is the strategy, and this is what you will see during this presentation. We can move now toward the sustainable biphasic system. So it's not only a sustainable solvent, it's a biphasic system. In the literature, what you have found is systems based on DES using heptane and ethanol. If we want to invent new stuff, we have to get from the old stuff, right? So what the literature gives is heptane, ethanol, and type 3 or type 4 or type 5, eutectic solvents. You'll recognize them here. And our research strategy is to first change one solvent, one organic solvent, and then change the second one. So we go we take the easy step first, ethanol, because ethanol is more polar than heptane. When we have such system, heptane ethanol deaths, where for what you see a typical ternary diagram here, usually heptane is in one phase and ethanol mostly in the other with deaths, and ethanol sometimes partition between heptane. So we just first change the polar system, and then we will try to replace heptane and ethanol. What I will show you more here, is heptane with other solvents. So what we do first is try to reobtain those data from the literature and then others. Usually you have a ternary diagram, but as I just say here, we have actually two independent variables, which are the weight percent of heptane and death rate, which means we can show those ternary diagrams as binary diagrams. So we carried out, we measured binaural curve using a simple cloud titration point method. And we obtained here 3 different systems. These are a few examples of the system that we studied: heptane ethanol and a death based on choline chloride with ethylene glycol, levulinic acid, or glycerol. We obtained nice binaural curves. They are very close together, most of them. If there was not choline chloride, we would still have a binaural curve. So it's not always necessary to have a death. Even just the HBD, ethylene glycol, levulinic acid, might be enough to have a phase separation. I'll just show here a point corresponding to a mixture that we will use later when we want to separate, to extract, or partition, to be exact, a natural compound between 2 phases. Anyway, if we want to change now ethanol with butanol and ethyl acetate, we use a less polar second solvent, butanol or ethyl acetate versus ethanol. And what you obtain is those kind of curves. So the first thing that you need to know, the gray curve here is the one that was before. It was heptane ethanol levulinic acid. And you see that when you add butanol or ethyl acetate, the monophasic domain that is here on the left side compared to the biphasic domain on the right side, this monophasic domain becomes much larger, which is not necessarily very good for us because we obtain a monophasic domain. So we don't have two immiscible phases, and extraction or partition cannot occur. What we can see that the more hydrophobic the death compound as well, the smaller the biphasic domain. So similarly to the less polar solvent, butanol, ethyl acetate, when you use thymol and levulinic acid, then you increase also the biphasic domain. I didn't show all the curves because it would have been not clear enough. But if we have those with choline chloride, the biphasic domain is a bit larger. Anyway, this is to see that we can experimentally measure those binaural curves and play along with the different solvent to have a biphasic domain that would be as we want it. Once we have that, the next question is, what are the phase compositions? So a phase composition is when we are here in the biphasic domain. If we prepare a mixture, then the mixture will split in 2. Splitting in 2 means we'll have a lower phase in general that is rich in death, while the upper phase will be rich in heptane. Okay? These are typical tie lines. So tie line and Cosmotherm results as well. What we see is that Cosmotherm works pretty well. You see that the theoretical binaural curves here, the white points are merging pretty well with the experimental one. It also worked when we had choline chloride. So since we have only 20-25 minutes, I'm not going into details into how do we describe the choline chloride, but I might answer the questions if you want. One assumption in that is that choline chloride and levulinic acid remain together in the theoretical description of the system. All in all, this works pretty well. Now, the question is the phase compositions here, they are theoretically calculated by Cosmotherm. I will show you that we can measure them experimentally. So in general, there is a good description of the phase diagram using Cosmotherm. Of course, it is not always the case. If we move to a bit more problematic solvents, meaning less polar solvent, ethyl acetate, you see that there is a start of a discrepancy between the experimental and the theoretical curves. It's even worse when we move towards thymol levulinic acid between heptane in a system based on heptane, ethyl acetate, and these tests. Here you see several problems. It works on the top here, but then there is a big discrepancy. And then the biphasic, the tie lines measured by Cosmotherm are very wrong here. This point should not be there. One assumption that we made here also is that not choline chloride here, thymol and levulinic acid remain together, which is a problem with the type 5 test, because the type 5 contain a hydrophobic compound, thymol, and hydrophilic compound, levulinic acid. And this fails because we describe that as a ternary diagram in which thymol and levulinic acid remain together. And this is the problem. What we have to do is describe that. So when we want to describe this system as a ternary diagram, it fails. We need to describe it as a quaternary diagram with actually heptane in 1, in 2 it's ethyl acetate, in 3 it will be thymol, and in 4 it will be levulinic acid. And what we can see is that Cosmotherm is able to describe a biphasic domain in 3D, if you want, in a quaternary diagram. What you can see is that I calculated the phase composition of these two immiscible phases. You have in this phase more levulinic acid than thymol, whereas here you have a large excess of thymol compared to levulinic acid, meaning that the thymol and levulinic are partitioned separately, and this explains why it fails in this simpler representation of the binary. So the next step is to study experimentally the phase composition. Actually, what Cosmotherm does, that very simply it calculates the binaural curves and can give you tie lines without problem. Experimentally, it's more complicated. And what we had to do is develop an experimental method for analyzing them, and it's done in 2 ways. Heptane, ethanol, butanol, and ethyl acetate are calculated using GC, gas chromatography. We actually measure the KD in both phases, and because we know the volume and the density of each phase and the total amount of ethanol of each solvent, we can get back to the composition of each phase. For levulinic acid and choline chloride, because they have a very high boiling point or no boiling point at all, very low vapor pressure, we had to use HPLC. And we do exactly the same way. And we have, see, typical example, we have a big peak for choline chloride and levulinic acid. Most of the time, we have to dilute these samples in order to not saturate the columns. When we have done that, we can now compare experiment with theory. So if we take this point on a ternary diagram of a system like that, what we can obtain is that we will just here use systems based on heptane, ethyl acetate or butanol, and levulinic acid or choline chloride levulinic acid, not yet thymol levulinic acid. What we see, so we get the experimental data, which are the full composition of each phase of this mixture, biphasic mixture. The only thing that I wanted to show is that as soon as we add the choline chloride, as soon as we form a test, we expel actually here its ethyl acetate from the bottom phase toward the upper phase. We have more ethyl acetate in the upper phase and much less in the lower phase. Similarly, when we have butanol and a DES, there is more butanol in the upper phase and less butanol in the lower phase. This is interesting because it shows that we can very simply change the whole composition and presumably the partition of a natural compound if we use it. Now, what I want to show you is similar systems and what experiment and theory gives. So we use this system with butyl and a DES with the choline chloride and another DES with thymol. Levulinic acid is always here. So this is the 2 phases. Experimentally, we get those proportions. These are weight %. So we won't get into the whole details, right? But it's just to show you that what we measured experimentally here, well, is pretty well, there's of course a little mistake here, is pretty well described by Cosmotherm. The data, the calculated proportions are pretty close to the experimental one. and even with a thymol levulinic acid system, which is a bit more problematic than choline chloride. So all in all, Cosmotherm is pretty efficient on describing these phase diagram and binaural curves. So we have normally completed that task. We have binaural curves, so biphasic systems, and we know exactly how they are composed. And we can describe that with Cosmotherm. If we do partitioning of these natural compounds, for example, we took those typical model compounds and we used them and with these type of biphasic systems, and we partition them. We do not extract those compounds will partition between these different systems. So what we can see here, just as a fast reminder, here it means that apigenin is mostly in the lower phase, while tocopherol is mostly in the upper phase. Upper phase is the heptane phase, so it's the apolar phase. Experimental results and calculated results. What is very comforting is that the trends are followed. Tocopherol is always in the heptane phase, apigenin is always in the lower phase. And those compounds like coumarin are actually pretty well described compared to the experimental results. So if we combine these two graphs together, what we have is that. So those should be compared by pairs. Okay, I just merged the two previous plots, histograms. What you see that in general, it follows pretty well. Calculated results follows pretty well experimental results. And this is from a qualitative point of view, satisfying enough. There's a general agreement. So now that works, the question is how do we use that in CPC? So the first task that we have to do when we collect all these KDs for such samples is what system here am I going to take to try to separate all these compounds together? In red here, you can see that this system with heptane, butanol, and this test appears to be optimum for separation application into CPC for separating these compounds. Why? Because the KD are not too low, not too high, but they are pretty different. So if we do that now, we are going to apply this system specifically to the CPC. So the strategy is the following. We use a mixture of those 4 compounds in a concentrated mixture. We prepare a biphasic system based on this solvent and this test. We load the phases within the CPC. One will be the stationary phase, the other one will be pumped in it and eluting as a mobile phase. We recover each fraction, each 45-second fraction that we analyze by HPLC. And what we obtain finally is a diagram like that kind of plot. The time being the elution time, and what we see is that we have different peaks corresponding to each compound. So without going into too many details, this really shows that we have pretty easily been able to separate all those 4 compounds. Of course, this is a model solution. It's easier when you have 4 compounds. The next step will be further. If we have a real extract, what will happen with CPC? So there is a good separation of these 4 compounds, and of course, also about to mention the conditioning, like the flow rate or the rotation speed, needs to be optimized, and this is an ongoing work. So at the application to CPC, as a short conclusion, there is a partition coefficient that are satisfactorily described using Cosmotherm, which is a good thing because measuring those KD is tedious and time-consuming. And also, from an experimental point of view, organic biphasic systems can be used in CPC for purifying natural compounds. If we want to do that, we would need it previously to carry out the whole experiment and then end up with, can we use that system or not? The question is, can we move towards a predictive strategy using Cosmotherm? So this would be the last part of my talk. What we want to do is to use Cosmotherm as a fully predictive tool to find a suitable system, biphasic system, for separating natural compounds. Ideally, it would be from a raw material. So there was some preliminary work done in the lab on the extraction of Rosa centifolia using a death-based extraction system. Chemical analysis gave the composition of our extract. You can find that in the literature, of course. We just showed that our extraction was as expected. And then can we propose a biphasic system based on DES in order to selectively separate those compounds, or at least groups of compounds? So the strategy here, because there's a very large screening, imagine we have 3 different solvents, and each solvent can be changed as we want. So we just focus on a biphasic system based on the DES containing choline chloride and levulinic acid, because up to now this was the one that has been the most studied by us and giving the most promising result. What we do, we keep heptane for the time being, and we choose between ethanol and butanol. The thing that what we do is not just using one concentration of ethanol. We see the influence of the concentration of ethanol or butanol on the partition coefficients of each of these natural compounds that we have in the rose extract. And then, of course, what we do is calculate the partition coefficients. So we have those kind of curves. Here, this is how we obtain the different composition with a given amount of ethanol varying between 0 and 40%. We describe or we predict different systems, right? And we calculate the KD of all these compounds. So what we can see here is the results of KD for each natural compound present in a rose extract, according as a function of an increasing amount of ethanol in the biphasic system. KDs here all decrease. We have not shown citronol, that would have been a bit before 1, but everything decreases. And you can see that the higher the concentration of ethanol, the closer the KD values, which is not good for us. According to that, we could choose maybe 10% or 10% of ethanol in this biphasic mixture as a good solvent for separating compounds. If we move to butanol, just changing ethanol to butanol, the behavior is completely different. And here, KDs, representing the y-axis, diverge more and more as we increase the amount of butanol. Of course, we could imagine that increasing the apolyl solvent in this kind of biphasic system has an opposite effect as increasing the ethanol polar solvent into this kind of biphasic system. But still, it's still interesting to see that with butanol, some compounds do increase a lot. The KD of some compounds increase a lot, where others do not. From here, what we could see that heptane butanol appears a promising solvent for separating compounds from the rose extract, and especially maybe take the one that has 30% butanol, because the KDs here are more different. We could at least obtain probably 4 different families of compounds, these 2, these 3, or these 2, and these 1 or these 2. So this is just the story of what we've been trying to do. And of course, this implies the next step for us is to prove experimentally that these kind of systems work. So as a conclusion, I think, or I hope I managed to show you that organic biphasic systems are a good system that can form with many DES, that it is possible to measure the phase composition using techniques that are not so complicated to use. Partition of natural compound generally follows the KO values, but we have some surprises. I didn't enter into details. We can talk about it later. The systems are applicable to CPC processes. Because of the time, I didn't tell you that it is very important to pay attention to viscosity and pressure within the water. This is why we used biphasic system containing organic solvents to decrease the viscosity. And that cosmotherm is efficient in this system. I'm not saying it is efficient in all systems, but at least for these systems, it is suitable. And I would like to thank you. I would be open for any questions related to this topic. Thank you.
Thank you very much, Nicolas, for this nice presentation and very interesting results. So feel free to ask the question. We have already some questions in the chat. So from Philippe Bertrand, it asks you if any predictable candidate, if there are any a predictable candidate to replace heptane, which could be also one of my questions. Why not trying to substitute the heptane? And the type of CPC equipment you used.
Thank you. So yes, I have to answer for those two questions. Yes, we can find candidates. Now, of course, we wanted to go step by step. We try not to turn the table immediately, but yes, there are some even biosource chemicals that methyl THF, for example, that even though a bit soluble in water could be used, or CPME or others. They should be used without any problem, in my opinion, in CPC, which is something that we are actually going to carry out very soon. And as for the CPC equipment, we use a CPC 50 from Armen, which is now Gilson, which is why we have those photos, for example, here. So this is actually the CPC that we are using.
Yes, Philippe agree with the methyl THF, yes. Of course. It was also my question: why did not replacing heptane, which is the bad one, the bad yes. guys in the system,
very true.
and focusing in ethanol? And I have also one question, also dealing with the more precisely parameter in CPC. How about the flow rates you use, and also which back pressure do you obtain and the rotation speed? Because I guess with this choline based phase, it could be really high.
So for the flow rates, I think we used a few milliliter per minute, or maybe yes. at some points it was half a milliliter per minute, okay. just to really try to collect, to purify as much as possible one of the compound that was complicated. So this is one thing. The other thing is that yes, it can be tricky with the back pressure. Usually you can go up to 50 bars. We usually go to 40, 45. We had a bit of an overpressure at some point, so the CPC just calmed down.
Yes, I guess so.
The good thing with those systems, and this is why we have ethanol, and it's a bit trickier with butanol because the viscosity of butanol is a bit higher than ethanol, is that because we have at least 40 or 20% of this organic solvent, the viscosity of the lower phase decreases up to really acceptable values. If we had pure DES with choline chloride, it would never go into the capillary, into the column. Voilà.
Okay, and we don't have any other question. I have one more. Did you consider to introduce non-polar NADES? Because by the moment you are focusing on
we are,
and
actually, very true. As I said, we were trying to go step by step. First, use simple, so to say, classical DES. Maybe you have seen, I don't know if you still see my screen, but here, I don't know if you see it.
With the timer.
Well, yeah, with the binodal curves, you can see that as soon as you use type 5 DES with those menthol or thymo one, the biphasic domain becomes much smaller. So we have to shoot at the right biphasic mixture. But I'm pretty positive that with the right mixture, we'll have a simpler application to CPC, because those type 5 DES are much less viscous than the choline chloride based ones. It's the next step that we'll carry out.
It's the next step.
Soon.
Okay.
Yeah.
We have another question. Do you think running both Cosmotherm and Cosmo RS, they give, if you run both, they give the same prediction in estimating aqueous solubilities and activity coefficients in combining polar and apolar DES?
Alors, this is a good question, but it's a tricky one. Carrying out calculation with Cosmotherm to get biphasic domains and phase composition, and especially partition coefficients, is less actually problematic than estimating solubilities. Why? Because actually, when you make a partition, when you have a partition coefficient, you make a variation of kind of solubilities or of activities coefficients. When you use just the solubilities, you maximize actually the error because you don't have this delta. And I wouldn't recommend very simply to use Cosmotherm raw just to measure solubilities, because from my experience, Cosmotherm just gives trends, and the solubility that it gives, especially in water, especially in DES, sorry, it's less problematic in water. They are not very reliable compared to experiments. But as soon as it is a partition between two phases, then the results are surprisingly satisfying. Note that the data that I showed you are in log KD though, right? So you can have 50% mistake, but it's not a problem for us because we are not focusing on a specific absolute value of a partition coefficient, the trends different in partition coefficients. I hope I answered to Mike.